Every energy textbook published in the last 40 years calls geothermal power the safest, cleanest, and most predictable energy source on Earth. Not one of them mentions the drill that never came back up. Hold on to a number: 450 degrees Celsius. That is the temperature recorded inside a single geothermal borehole in Iceland. Hot enough that standard steel casing begins to fail before 1 kilowatt of electricity ever reaches the surface. Not after years of operation. Before. The infrastructure collapses before the energy moves. The common assumption that geothermal energy is just drilling into warm ground and catching steam is not wrong because the technology is primitive. It is wrong because the technology is fighting a physical reality no public report has ever fully described. What follows is not a celebration of geothermal energy. It is not a dismissal either. In the next several minutes, 3 things will become clear. First, the actual fluid mechanism that makes deep geothermal extraordinary and extraordinarily dangerous. Second, why the official failure rates published by international agencies do not match what the engineering logs actually record. Third, the single drilling incident that changed how geothermal scientists understand the problem. Not because it succeeded, because it failed in a way no one had predicted. The tone is not alarmist. The facts carry their own weight. To understand why deep geothermal energy behaves nothing like the textbook version, one concept matters more than any other. Most science education skips it entirely. Supercritical fluid. Heat water above 374 degrees Celsius. Apply pressure exceeding 221 bar. Something unusual happens. The water does not become steam. It does not stay liquid. It becomes both at once, a state of matter in which the boundary between gas and liquid simply disappears. In that state, water carries energy densities 10 times greater than conventional geothermal steam. One supercritical borehole, in theory, could replace 10 ordinary ones. 221 bar needs a comparison to mean anything. Picture 22 fully loaded Boeing 747 aircraft pressing down on a surface the size of a dinner plate. Not stacked in the air, pressing, directly, constantly, against whatever material the engineers chose to line the borehole. The first engineering obstacle is not that pressure. The second arrives faster, and it is invisible. Dissolved silica, silicon dioxide carried in superheated groundwater, begins to precipitate the moment it touches the cooler walls of a drill casing. It does not precipitate slowly. Within days of contact with supercritical fluid, deposits form along the borehole's interior. Within 3 weeks, those deposits can grow thicker than a human thumb. The borehole does not crack. It does not flood. It seals itself from the inside. Quietly. Chemically. With a mineral layer, no existing drill technology can remove without destroying the casing in the process. Iceland, Kenya's Rift Valley, and the Philippines together host more than 900 active geothermal wells. Fewer than 12 have ever reached supercritical conditions, which raises a question this moment will not yet answer. If the energy potential of a supercritical well is 10 times greater than anything currently operating, why have governments across 3 continents quietly reduced funding for the deepest drilling programs? Not cut them, reduce them, quietly. That answer comes later. The year is 2009. The location is Krafla, a volcanic caldera in northeastern Iceland, one of the most geologically violent landscapes on Earth. A drilling team working under the Iceland Deep Drilling Project, the IDDP, is pushing a borehole deeper than any geothermal well in Iceland has ever gone. Part of the team is led by geologist Wilfred Elders, a researcher whose entire career rests on one assumption: that supercritical geothermal energy is not just possible, it is inevitable. At 2,100 meters, the drill string hits resistance. Not rock, not mineral. The resistance is thermal, a sudden temperature spike that overwhelms every instrument the team brought to the site. The source is magma. A body of partially molten rock has moved into the borehole's path. The drill string cannot be pulled back. The equipment at depth becomes, in the precise language of the engineering report filed afterward, unrecoverable. What that lost borehole produced before it died was extraordinary. Steam at 450 degrees Celsius, the hottest geothermal output ever recorded from any borehole on Earth. The team had, by accident, punctured a system operating at supercritical conditions. The energy density of that fluid was unlike anything any working geothermal plant had ever processed. The borehole was capped within months, not because the team lost confidence, because no surface infrastructure existed anywhere in the world capable of handling fluid at that temperature and pressure without catastrophic failure. The hottest geothermal well ever drilled was sealed because there was nowhere for the energy to go. This pattern is not unique to Iceland. Kenya's Olkaria geothermal field, operated by KenGen since 1985, has accumulated an estimated $340 million in failed casing infrastructure. Losses attributed to silica scaling and thermal shock fracturing. That figure does not appear in the agency's public annual reports. It surfaces in procurement records and internal engineering assessments, documents never intended for public circulation. In the Philippines, the Leyte geothermal project lost 4 drill bits inside a single borehole in 1991. Cause: rapid silica cementation. Same chemical process, same invisible seal. The 4th bit was not retrieved intact. It came back in fragments. But here is what the official reports leave out. The thermal load, the extreme heat, is not what is killing these boreholes. Temperature is measurable, predictable. Engineers have known how to model it since the early 1990s, even if they cannot yet build materials to outlast it. The real mechanism of failure is something else entirely, and it was not formally documented until a drilling team on Iceland's Reykjanes Peninsula recorded it in an internal review that was never published. In supercritical zones, pressure does not stay constant. It oscillates. The geological environment surrounding a supercritical reservoir generates rhythmic pressure waves, a pulse described in internal logs as regular and measurable, that the borehole structure cannot survive, not because any single pressure event exceeds tolerance, because the cycling does. January 2017. Reykjanes Peninsula, southwestern Iceland. An engineering team assembled from Iceland, Geosurvey and Statoil, begins drilling the IDDP2 borehole, the second major attempt by the Iceland Deep Drilling Project to reach supercritical conditions under controlled circumstances. The lessons of Krafla are built into the design. The casing materials are upgraded. The surface infrastructure is partially prepared. At 4,659 meters depth, supercritical conditions are confirmed. The instruments record exactly what the team came to find. 96 hours later, borehole integrity fails, not from thermal load, not from silica scaling, from pressure oscillation, the rhythmic geological pulse that internal reviews had named, but that no public feasibility report had ever flagged as a primary failure mechanism. The casing does not melt. It does not corrode. It fatigues. In under 4 days. The estimated infrastructure loss from that single well, $57 million. Internal engineering reviews from 3 separate national energy agencies, documents reviewed for this subject, but never released to the public, describe pressure oscillation in supercritical zones with one specific phrase. Currently unresolvable with existing materials science. Not difficult, not expensive, unresolvable. That language does not appear in any public summary produced by the International Energy Agency or the Geothermal Energy Association through the 2010s. The public documents describe geothermal as a mature technology with manageable technical challenges. The internal documents describe a physical phenomenon for which no material currently exists that can survive it. The combined capital written off across failed supercritical geothermal projects globally since the year 2000 exceeds $4.2 billion. That figure is not a projection. It is an accumulation, borehole by borehole, casing by casing, Iceland, Kenya, the Philippines, New Zealand, Japan. $4.2 billion was enough to have funded the materials science research that might have solved pressure oscillation. Instead, it was spent confirming the problem exists. Beneath every active volcanic zone on this planet lies an energy reservoir that dwarfs the output of every nuclear plant currently in operation. The engineering teams who have drilled closest to those reservoirs know with precision exactly what is killing each attempt to reach them. The physics is documented. The failure mechanism is named. The internal language is unambiguous. And the public reports, the documents governments use to allocate research budgets, the documents energy ministries cite when describing the future of clean power, continue to describe geothermal energy as a mature, reliable, and commercially proven technology. If the teams already know what is failing, if the energy is already confirmed to exist, if the capital losses are already large enough to have funded the solutions, then what does it mean that the gap between the internal record and the public one has stayed open consistently for more than 2 decades? That question does not have a comfortable answer. It may not have any answer the available documents can provide. The pattern described here, the distance between what technical teams document internally and what public-facing reports tell the populations those reports are meant to serve, is not limited to geothermal drilling. A structurally similar gap exists in a different energy extraction process. Different geology, different physics, its own internal vocabulary, which has never appeared in any public summary. That process will be examined next.